Good evening, dear students. Welcome to AS Engineering College YouTube live sessions. In this series, we are actually going through the revision series of the previous year questions in applied physics subject. And we have finished the first unit and we are already through almost half part of the second unit. Now the other half, so we're going to cover today. What do we have to cover in today's session? So the first one would be light emitting diode, and then the second one is solar cell, and then followed by a pin photodiode, and then we close with bipolar junction transistor, that is BJT. So these are the four topics that we will be discussing in today's session. I'll be starting first with the concept of the types of semiconductors before we actually head to the light emitting diode. Because in the previous classes from the second unit, we have understood how a p-n junction is formed and how a diode works. In fact, we have seen two different types of diodes, their construction and working. One, the normal p-n junction diode, the other one is the Zener diode. We understood how would be their working, how would be the characteristics and all. Now those particular diodes that we have used are the ones where they would be making the diodes either to work as a switch or to work as a rectifier when AC is applied to them. Now these diodes which actually produce light or which actually are photosensitive in nature are slightly different. In order to understand that difference, so what we're going to do is we're going to again classify semiconductors based on the output they give and how they behave and based on the material with which they are made. Let us see. Now semiconductors I am classifying here into two categories. One, the direct bandgap semiconductors. Two, the indirect bandgap semiconductors. So based on bandgap, we are actually dividing them. The behavior is entirely dependent on the bandgap itself. What are direct bandgap semiconductors? So semiconductors are two types, direct bandgap semiconductors and indirect bandgap semiconductors. Now I would be explaining this based on the graph, the energy level diagram corresponding to a semiconductor. We know the energy level diagram for a semiconductor would be consisting of the conduction band at the top followed by the valence band at the bottom. This is not simply an energy level diagram corresponding to a semiconductor, but also it's a diagram which is involving the energy vector E and the propagation vector K. So here I am talking about energy of the particles. So this is the energy on y-axis and the propagation constant on x-axis. Now the graph between E and K is a parabola which we have seen in the first unit when we have discussed about EK diagram just before the concept of effective mass. Now that particular parabola would be like this for conduction band, and in case of valence band the parabola would be inverted just like this, just to show that there will be more number of energies existing when the energies are lower in valence band. As the energy gets higher towards the top of the valence band, the number of energies so that would be accommodated to those particular charge carriers would be reducing. Similarly, here also in case of the conduction band, the parabola actually shows that the energies are distributed in a way that as you go higher with the energies of the charge carriers, so that higher the energy, automatically more number of charge carriers would be fitting in. That is shown by this parabola. Fine. What we are going to understand using this parabola about direct bandgap semiconductors? Now let me tell you, did you just observe in this particular diagram that this is the bottom of the conduction band, I mean to say the minimum energy of the conduction band, and this is the maximum of the valence band, and they are lying on the same line, right? So they are lying on the same line. Those materials in which the minimum energy of the conduction band coincides with the maximum energy of the valence band for the same value of K, Did you see? This is also K line, this is also K line, and these two actually are the same point. So just like it's just a line joining them would be a straight line. That means they are lying along the same place itself. So that means for the same value of K, the minimum of conduction band, I mean to say the minimum energy of the conduction band and the maximum of the valence band, the maximum energy of valence band are existing. Those materials in which this happens are known as direct band gap semiconductors. Now that is what. So I would erase this as you can see through this line, that the minimum of the conduction band is going to coincide with the maximum of the valence band. Those materials in which this takes place are known as direct band gap semiconductors. That is what. So the minimum energy of CB here refers to conduction band. So let me tell you this, I have made it a shortcut. CB means conduction band, VB means valence band. Now the minimum energy of CB conduction band coincides with the maximum energy of VB for the same value of K. Those materials which actually have this particular property are known as direct band gap semiconductors. Now coming to indirect band gap semiconductors, so I would have to explain about the similar graph, and it's quite clear as you can see the same EK graph. So there is a difference compared to that of this one. What is the difference that we are having compared to that of this one? Just see the minimum of the conduction band, I mean to say the minimum energy again, and the maximum of the valence band are not lying along the same line, means they are occurring at two different values of K. They are occurring at two different values of K, right? So that means, so they are different from these materials. How do we call them as? So indirect band gap semiconductors. As you can see, there are two lines that means the maximum of the valence band is occurring here, the minimum of the conduction band is occurring here. So therefore, this is an indirect band gap semiconductor. So which you can understand by means of this statement. The minimum energy of CB conduction band does not coincide with the maximum energy of valence band for the same K. Clear? So this is how we actually define the direct band gap and indirect band gap semiconductors. But there is something more that we need to discuss about these two the materials. So we'll be moving on to the next slide. So I'm going to talk about the direct and indirect band gap semiconductors, starting with the direct first. In these materials, EH recombination, I mean to say electron-hole recombination, takes place directly from conduction band to valence band, resulting in light. What I mean to say, I'm going back to again the energy level structure. So where you would be finding conduction band and valence band. What do you have in the conduction band? The free electrons. These are the free electrons. I'm showing with one pair of an electron and a hole. This is a hole that is existing in the valence band. So you are very much familiar with the understanding of p-type and n-type materials. There will be free electrons in the material which will be shown all the time in the conduction band. Conduction band is actually the ranges of energies of the free electrons. Conduction band is a band of energies of free electrons. Now coming to valence band. Valence band is a band of energies of the, you can say, the holes that are existing in a covalent bond. In fact, they are going to almost the same as that of the valence electrons. The holes would be having the energies same as that of the valence electrons, because where do the holes exist? Inside the covalent bond. How? The absence of an electron in a covalent bond, that is forming between two intrinsic semiconductor atoms, is what we term it as a hole. So therefore, hole's energy should match with that of the bonded electron's energy. Which electrons bond in an atom? Generally, the valence electrons. So therefore, the hole energy will be matching with that of the valence electron's energy. Right? That's why all the time we put holes in the valence band. It doesn't mean holes are going to exist here. Their energies exist here. So valence band is nothing but the band of energies of these holes, so which would be inside the covalent bonds that are formed between the valence electrons. Now coming to the conduction band, again conduction band is band of energies of electrons which are freely moving in between those particular semiconductor ions or semiconductor atoms. Now I am considering an electron here. This is an electron, and this is a hole. So what would happen in these materials? The electron-hole recombination takes place directly from conduction band to valence band. What would happen? The electron would straight away fall in the hole, so both of them annihilate each other. The transition would result in light. Understood? So what would happen physically in a material? Hole is going to go back, electron is going to go back to the hole inside the material. I think you are aware already. I need not have to go back to the concepts of how these electron hole formation would be and the recombinations would be, right? So one thing is quite clear. When electron automatically combines with a hole, it is going to produce light. Such recombination is termed as radiative recombination. How do we term it as? Radiative recombination. That particular recombination is going to produce light. Don't think all the recombinations are going to produce light, right? So if at all the material is a direct bandgap semiconductor, why do we call them as direct bandgap semiconductors? Quite simple. These materials are the ones where the transition of electron takes place directly from conduction band to valence band, resulting in light. So that is what. So therefore light would come, and this recombination is termed as radiative recombination. Right. So we understood light would come out because of this recombination. Now coming to the other side, indirect bandgap semiconductors. The EH recombination takes place via trap center, via a trap center from CB to VB. What we mean by this? But at the same time, this would result in heat also. Let us understand this one. So again, let us go back to this energy level structure, CB and VB. There is an electron in the conduction band, there is a hole in the valence band, and there will be a trap center. I need to tell you about these trap centers. When semiconductors are made, actually, we make use of the doping deliberately to actually increase the conductivity of the material. Because of doping, nothing but the addition of impurities, we are going to have charge carriers produced in the material. If you dope an intrinsic semiconductor with a trivalent impurity, we are going to have the holes as majority charge carriers. And if you dope an intrinsic semiconductor with a pentavalent impurity, you're going to have electrons as majority charge carriers. Thus, a p-type and an n-type materials are made. That is how they are made and that they are formed. Now the point is, here traps are nothing but impurities that are not deliberately added. Mind you, so while making the crystal, the original crystallization of these particular materials, semiconductor material takes place, some metallic ions may be trapped, sometimes the moisture in the form of the OH minus ions will be trapped inside the material. These are nothing but the impurities which are not deliberate in nature. So these impurities do exist with some very low, very small percentage, but these are the ones that can trap the charge carriers. So trap is such a one. So the trap center, these particular impurities would be having their energies lying between the energies of the electrons and holes for that particular original material. So a trap is nothing but an impurity having an energy between the conduction band and valence band. What does this trap do? If this trap generally traps electrons, it is called as the electron trap. If it traps holes, then it is called as hole trap. What is the example? Suppose if the material, so the impurity is a metallic ion. Let us suppose a sodium ion is trapped, is actually an impurity formed inside the material. Somehow it has been placed while the original crystallization takes place. Somehow it barged in while the original crystallization takes place. This Na plus ion requires an electron badly, and this is an impurity, mind you. This impurity is not deliberately added. Similarly, zinc ions would come, right? Such metal, copper ions may come. So while the original crystallization of a semiconductor takes place, these ions actually trap the electrons. And remember, the energies of these ions would be between the energies of the conducting electron and the electron that is there in the valence shell. And the free electron automatically falls into these traps. So that means, so the metallic ion would be trapping electron. Now what will happen if at all that kind of trapping takes place? So the electron would go to the trap, automatically gives out heat. And after some time, this electron would automatically come down to its normal position, that means the hole, and this, so that's the annihilation takes place of both electron and hole. Heat is produced. Now just observe the case here. One transition taking place from conduction band to the trap center. After some time, another transition takes place from this trap center to the valence band hole. We know one thing, when electron recombines with a hole, automatically no hole and no electron would exist. They cancel out each other. They annihilate each other. That's why, so initially when I've shown these particular diagrams, I've shown you the electrons and the holes. But when they recombine, automatically both of them vanish. What do we mean by this? Because no more charge carriers would be existing. Electron gone back to its original place, possibly where it has left. That means the deficiency. What is a hole? The deficiency of electron in a covalent bond. So if electron goes back to the bond would be restored. So hole actually gets cancelled. Electron, since it has gone back, that also gets cancelled. We are not going to have charge carriers, right? So that's why I've shown both charge carriers have automatically disappeared. Now coming back to these transitions. Now, there is a transition that takes place from conduction band to the trap center. Because when you just compare here, the transition took place from conduction band to valence band straight away, where this delta E, the energy difference, is large compared to that of the two delta E's here. Say, I would consider the energy, the transition, difference of energies between these two levels as delta E1 and the difference of energies between these two levels as delta E2. Now this is single transition. Automatically the wavelength would be small because as E is large, wavelength would be small. Automatically it would be falling in the visible region. We know visible region is from 4000 to 7500 angstrom units. So there light is going to come out. Light, if at all, if I say light has come out, means lambda values would be between 4000 to 7500 angstrom. Some people say it is from 3800, agreed. Okay, don't worry. So if at all you have to remember them as 4000 to 7500. No one will question, right? Now, coming to these two. Now since delta E is less, when you come, because that delta total energy is now split into two parts. One has delta E1, the other one has delta E2. What is happening here? The entire energy now become two parts. So if at all energy is less, this transition delta E1 is energy. So energy is definitely less than that of this one. So automatically the value of lambda corresponding to this transition, say delta E1 is equal to say lambda 1. Lambda 1 would be larger because delta E1 is smaller compared to that of this one. Suppose this transition gives out light which would fall in this range for lambda. This transition should definitely give out a particular value of radiation whose lambda would be greater than this. Understood? Whose lambda would be greater than this, because delta E is large, lambda would be this much. If delta E is small, lambda 1 would be higher. Higher in the sense that would be more than 7500 angstrom units. That means it is going to fall in the infrared region. The infrared radiation, nothing but heat. Understood? So this heat is also produced that way. So these are not radiative in nature. So we're going to have transitions of electron from conduction band to valence band via a trap center, through a trap center. Understood? So that's what actually makes the emission to be not as light, some other radiation. So generally the IR radiation which is in heat form. Now this is what we could term it as a non-radiative recombination. We term it as a non-radiative recombination. This is all about the direct and indirect bandgap semiconductors. We need to know what materials are direct bandgap, and then what are the applications of direct and indirect bandgap semiconductors. So one thing is quite clear, direct bandgap semiconductors are the ones where the minimum of the conduction band coincides with the maximum valence band for the same value of K. That is point number 1. Point number 2, in these materials, the transition of electron takes place directly from conduction band to the hole in the valence band, resulting in light. Now coming to the indirect bandgap semiconductors. Indirect bandgap semiconductors are the ones in which the minimum of the conduction band does not coincide with the maximum of the valence band. That is point number 1. Corresponding to the transition, the electron transition from conduction band to valence band takes place via a trap center. So I just considered only 2 particular transitions. There may be another trap somewhere here, there may be another transition there, and then to valence band hole. So automatically that corresponds to different transitions, resulting in higher values of lambda. So which would be falling in the infrared region, resulting in heat. So these particular transitions are known as non-radiative transitions. Such materials are nothing but indirect bandgap semiconductors. So we'll be moving further to understand what kind of materials would be direct bandgap semiconductor materials. Generally, so-called semiconductors that come to our mind whenever we think of semiconductors are not the direct bandgap semiconductors. Instead, we have gallium arsenide, indium antimonide, cadmium telluride, zinc selenide, cadmium sulfide. All these would be the best examples of the direct bandgap semiconductors. These are compound semiconductors. I think you might be knowing there will be semiconductors, the elemental semiconductors like silicon and germanium, right? Apart from that, there are many compound semiconductors like the 3,5 semiconductors. What are they? 3,5 means the third group and the fifth group, like gallium from the third group and arsenic from the fifth group. When these two are added, they are going to get the characteristics of a tetravalent material. So these are trivalent, these are pentavalent. When added, they are going to have the average of those two, the tetravalent material. So the tetravalent material is generally a semiconductor. Now, when gallium arsenide is doped with the pentavalent impurity, it is going to give N gallium arsenide. And when it is doped with a trivalent impurity, it is going to give us a p gallium arsenide. So when these two are chemically combined, you are going to get a p-n junction diode that is made with gallium arsenide. Understood? So that is how these diodes are made. In fact, I am going to go to those diodes later. Just talk about the semiconductors only. So this is a direct bandgap semiconductor. This is another direct bandgap semiconductor. Did you observe? These two are 3,5. These two are 2,6. So these are 2, 6. Again the same thing. The second group and the sixth group. So when they are combined with each other, they are going to give the average 2 plus 6 by 2. So what is that? 4, right? So the tetravalent nature. So these are called as 2,6 semiconductors, the compound semiconductors. There are various such compositions, so which actually have the transition taking place in those materials from conduction band to valence band directly. They are direct bandgap semiconductors. Let me tell you a secret here. When electron is going to combine with a hole to give light, that's the question. Now, when the crystal momentum of electron matches with that of the crystal momentum of hole, then automatically they shake hands with each other and combine to give out light. What is that? When the crystal momentum of electron matches with that of the crystal momentum of a hole, then they recombine to produce light. I am not telling you anything new here, even though I spoken it as a secret. Why? Because in the previous slide, what we have seen is, I am going back to the previous slides. This one, just before this one even. This one. In the previous slide, I am talking about crystal momentum. This is crystal momentum. Remember K for crystal momentum, right? Because you would get the momentum of the particle, say if you write it as P, in quantum mechanics we write it as h cross K. H cross is a constant, h by 2 pi. K is the one that decides the momentum of the particle. So How come? Because you can just write this one as h by 2 pi. This k as 2 pi by lambda. When you cancel these two, you are left with P is equal to h by lambda, which is de Broglie's equation. What is that? This has come from lambda is equal to h by P. De Broglie equation, right? So that means, so the momentum of the particle is related to k by means of this entire process. So you can call that k as crystal momentum since it decides momentum of the particle, right? So this k is nothing but the crystal momentum. So the crystal momentum is the one, if it matches for these charge carriers, when they combine, they are going to produce understood? So that's why the direct bandgap semiconductors are the ones when transition takes place for an electron from conduction band to valence band, then thus that is going to give out a hole. Right. Moving further, I am going to go to the next slide. So all this we have completed. We understood there will be radiative and non-radiative transitions, and we have seen the materials which are direct bandgap semiconducting materials. Now for this indirect bandgap semiconductors, the materials are elemental semiconductors like silicon and germanium. In these materials, let me tell you, silicon and germanium, the transition will not take place directly. So that's why these materials are not preferred to produce light. So you cannot make a particular light emitting diode using silicon or germanium. Let me be fair. Excuse me. So you can make a light emitting diode or even a laser diode using these materials only, because the transitions in those materials would be resulting heat, not light. Okay. So I would erase this portion. What next? Applications. As I have told you, these materials should be the ones which are used to make the devices which give out light. What are the examples? Lasers, LEDs, right. Now how about these materials? They are not useless at all. They would be useful to make, they make junction diodes, to make the transistors which are used as amplifiers, oscillators, or even rectifiers and switching circuits. So in all that, these particular materials are used, the normal PN junction diode, the transistors and all. So silicon and germanium are used to make such particular devices, whereas the gallium arsenide, indium antimonide, the 2,6 semiconductors are used to make LEDs and laser diodes. So we got a clear idea. If at all we discuss about an LED, that LED is definitely made up of what material? Spot on. You're right. Direct bandgap semiconducting material like this or this. Understood? So till now we have discussed about diodes. So I'm going to discuss about transistor also at the end of this particular session. These are made with indirect bandgap semiconductors. But just before that, BJT, I'm going to discuss about 3 particular devices which actually involve in either the production of heat or production of light or detection of light. Production of light or detection of light. Photosensitive nature they have. So let us see them one by one. Since we are discussing questions and their relevance, our topic is relevant to that only. So we have got questions that are being asked, and how do a question come on LED? Explain the construction and working of LED. Here, this was asked in AS. A, we know how would be the notation. A corresponds to AS R20, November 22, and there is a supplementary paper in April 23. The same question has appeared. J corresponds to J into H paper. So that was asked in R18 regulation, April 23, June 22, October 21. It seems to be a stock question, right? So therefore we should know about it and how to interpret that one. So I'm moving forward to discuss about the working, the construction of a LED. You know what is meant by LED, right? Light emitting diode. So I'm going to come across this light emitting diode. What is a light emitting diode? If I just close all this, you should be in a position to tell. Definitely light emitting diode is a PN junction diode. Made up of what? It should be made up of a direct bandgap semiconductor. Then only it can emit light, right? So a forward bias PN junction that is made up of a direct bandgap semiconductor is what we term it as a light emitting diode. Now, due to this forward bias, electrons from the N side and holes from the P side are going to diffuse to the junction. We have discussed about the forward bias and reverse bias when we discussed about the PN junction diode. We know that during forward bias, because of the repulsion, the charge carriers would move towards the junction and automatically, so they cross over the junction, resulting in the net conductivity of the material. So there will be current during forward bias. Now in these kind of materials, the charge carriers, while they come to the junction, they recombine with each other. When they recombine with each other, we know if at all it's a direct bandgap semiconductor, light is going to come out. That's what. They recombine to produce light. This is the general representation of a junction diode. So this is the P side and this is the N side, where there is a line that is N side, right? Now this is the representation of a LED. What difference it will make? Yeah, arrows as you've seen, right? These arrows actually indicate light is coming out from that diode. So in a circuit, if at all you have to make use of the circuit symbol for LED, this is the one, okay? Now this is how the LEDs appear, right? Different colors, okay. Moving forward, construction. Now when you talk about an LED, the N-type layer is grown on a substrate and a P-type layer is deposited over it and a junction is formed between the two layers. Didn't understand, right? I'm going to tell you now. So now consider a substrate generally made up of one kind of a semiconductor, maybe neutral region, you can call it as substrate. Now on which an N layer is grown, right? How this takes place? There are various ways. So there is a diffusion, there is grown junction, so there is fusion, and there is epitaxial growth. All these are different types of ways that we grow a particular kind of semiconductor over a substrate. N-type material is grown over the substrate, and then a P-type material would be formed, so also made to develop over that particular N-type material. And in between these two, we know what would form junction, right? So this is a substrate on which there will be N-type material. We know N-type material will be consisting of electrons as majority charge carriers, electrons as majority charge carriers. P-type material consists of holes as majority charge carriers. Now when these, okay, for light to escape from the upper surface, it is left free in a way that the metal contacts are made with the outer edge of the P layer. You'll get to know when I actually show that there. The first one you just observe, N-type layer is grown on a substrate. That's what you have seen. P-type layer is deposited over it, and in between there is a junction formation, fine. Next, for light to escape from the upper surface, for light to escape, more upper surface is left free in a way that the metal contacts are made at the outer edge of the P layer. What do we mean by this? So if at all this is a diode made up of a direct bandgap semiconductor, when it is forward biased, it is going to give out light. Where it is going to give out light? At the junction. Because where the recombinations take place? At the junction itself. Electrons from N region, holes from P region are going to combine with each other. They're going to come and recombine, and light is going to come out. But remember, junction region would be very thin. So therefore, what we do is, we're going to make P-type material very thinner, so that light is going to come out from P side. That means we need to keep, P would be almost very thin, at the same time transparent in nature. We keep P material in a way that, we have to give forward bias. Forward bias means P side is connected to the positive terminal of the battery, N side is connected to the negative terminal of the battery. That means we have to have a contact here, an electrode. So what we call it as an anode, right? So how that anode would be for p-type material? This is how it would be. Why? Because light would come out. If at all I close this one entirely with a plate, light would again reflect back towards the junction. But we want light to be emitted, light emitting diode, right? So therefore, so these are the contacts. Similarly, there will be a complete closer here for cathode, just below the substrate. So for making cathode connections, a metal film is coated at the bottom of the substrate, just like this. It is a complete film, complete plate, a metal plate you can call it as, right? Because light will not come out in this particular direction. We want light to come out only in one direction. So that is this way, above, so the P layer, right? So that's why we made a provision for the light to come out. We just considered only the edges of the P layer, the outer edge of the P layer, so that we can connect it as an electrode. Right, how it would be? This is how it would be, the forward bias, as you can see. So the P side is forward bias, is having the positive plate, positive of the battery, and N side, so through that substrate, is going to be connected to the negative terminal of the battery. Right, this is how the construction of LED can be considered. Moving further, we're going to discuss about the working of LED. What would happen when forward bias takes place? When the junction is forward biased, we know, so the material, when junction is forward biased, electrons from N side and holes from P side move towards the depletion region and where they recombine. Initially, when there is no bias, there will be a junction formed, what we call as a depletion region, because there will not be any charge carriers in the junction at that point of time. But once forward bias is applied, automatically, let us suppose this to be the N side, this to be the P side, and there will be electrons in the N side and holes on the P side. They will be drifting towards the junction where they recombine with each other. So suppose that there is a hole here, there is a hole here, and there is an electron. So these two are going to recombine with each other. How do we show it in the energy level structure? So I'm going to show it in the energy level structure first. So during this process, energy is released because of electrons transition from conduction band, that is a higher energy state, to valence band, which is a lower energy state. So the transition takes place from conduction band to valence band. So when the transition takes place from higher energy to lower energy, energy has to be emitted, right? This energy would be emitted, but this would be in the form of light. Now, here, so this is the one, the electrons, the hole that is there in the valence band coming towards the junction would be combining with an electron. So that is how we show it. So an electron would be here, it is going to combine with a hole, and then they release light. They release energy that is in the form of light. So this is what is going to happen in a LED. How simple the working is. Why do we really bother about many things? The construction is so simple. There will be just 4 layers. Upon a substrate, there will be a P layer, which I haven't shown here, the substrate. In the previous slide, I have shown you in the construction, right? So there will be a substrate, there will be an N-type material, there will be a P-type material in between, there will be a junction anywhere. Now, once biasing is applied, the forward bias, what would happen? Electrons from N side and holes from P side are going to come towards the junction where they combine with each other, recombine with each other. That recombination in the energy level structure you would show by means this way. So electron in the conduction band and hole in the valence band, so are going to combine with each other. There will be transition of electron towards the hole in the valence band. Because of this transition, energy is released. What energy? Light. Which is released? Light is released. So I would write. Because of this one. Okay? This is all about the concept of working of LED. Okay? This gives you some idea about what would be the voltage required to produce light, and if at all we produce light, what materials actually produce what colored light. Here we have used, this is from a source from internet anyway. So gallium arsenide is the one that is going to give out radiation in the infrared region. So above 750 nanometers, 7500 angstrom is 750 nanometers. 7500 angstrom units is equal to 750 nanometers, right? So this is in nanometric scale. So gallium nitride, gallium lanthanide nitride is going to give us 450 nanometers, which would be just white color LED. If it is silicon carbide, it would be giving us blue color, that would be in, so that would be in between 430 and 505. Similarly, so there are several other materials. So I have just discussed about gallium arsenide only singly. Gallium arsenide singly is not used to produce light. It is used to produce infrared radiation. Generally, LEDs there will be infrared LEDs also. They are used for data propagation, data transmission through optical fibers. So there was a fifth unit where you would be studying about lasers and optical fibers. In optical fibers, you also come across, in fact, Venkatesh sir has discussed that with you about the fiber optic communication system, where light would be propagating through the optical fiber from the transmitter end to the receiving end of the fiber optic communication system. So that light transmission takes place. Even though we say light, sometimes data is carried in terms of in the order of zeros and ones, and those zeros and ones will not be visible to us. So that data would be carried by an infrared light. So infrared radiation. So the radiation would be infrared in nature, which would carry zeros and ones through that optical fiber. Anyway, gallium arsenide, if at all, that is specially designed for it. Gallium arsenide is used, if at all it is used, it is designed only for data transmission in the infrared region. Whereas these are the ones which give those particular colors. So green color is due to aluminum gallium phosphide. And if at all you talk about yellow or orange color, it is gallium arsenide phosphide. So this is how different materials are going to produce different colors for an LED. Now I need to tell you one more point here. As I already discussed about the transition. So higher the energy of the transition, lower the wavelength. Higher the energy of the transition, lower the wavelength, which is evident from these two. As you can see, the lines are getting shorter as you move from 1 to 2 to 3. How can we say so? Higher the energy and lower the wavelength? Very simple equation is there with us. What is that one? Delta E is equal to Hc by lambda. Hc is anyway a constant as a product. H is Planck's constant and C is the velocity of light. So lambda and E are related this way. Higher the value of E, lower the value of lambda. So that's why in VIBGR, you're going to have blue coming first. So this is increasing order of wavelengths. Wavelength increasing. So blue will be having lower wavelength compared to yellow, orange, red or green. If you say blue color is coming out because of this transition, that is due to the transition energy is large, is higher. So as you see, if the band gap is less, automatically the transition energy would be also less and the wavelength would be higher. So it all depends on the band gap itself. So band gap is the one that decides the color of light that is going to come out from an LED. Okay? So this is the band gap as you can see. Right. Clear? For lower band gap, no, tell me, I'm going to close this one. Yeah, tell me. For lower band gap, higher would be the value of wavelength. Correct. For higher band gap, lower would be the value of the wavelength. If at all you consider only visible region, so red would come when the band gap is less. Okay? Okay. This is possibly about LED. We will move forward to discuss about IV characteristics of LED. IV characteristics are nothing but the characteristics of current and voltage of an LED. So current on y-axis and voltage on x-axis. We know light is going to be produced only when we forward bias the diode. It is made up of a direct bandgap semiconductor. When we forward bias, we have the forward current, forward voltage and forward current. And it's quite simple to understand that it is just like any other diode, a normal diode, where with increase in the value of the voltage, there will be increase in the value of the current, just like any other diode during forward bias. So different colors actually show whatever may be the color of the diode you consider, the scenario is going to be the same. With increase in the voltage, with a little supply of voltage, automatically the current is going to increase slowly initially, but once it reaches a particular value, so automatically it is going to jump exponential fashion. This particular current, or so this particular voltage, what we call it as threshold voltage for that particular diode. And this threshold voltage, as you see, is going to increase with color, so with decreasing wavelength. So here as you see, blue is at the end, so automatically, suppose if this is the threshold wavelength for blue, this would be the threshold wavelength for red. So which is occurring at a threshold voltage for red. So this is threshold voltage for red, and this is threshold voltage for blue, this is for green, this is for blue, and so on. So this voltage is the one that actually produces the sudden change in the current that comes out of the diode. These are VI characteristics or IV characteristics. There are one more characteristics that also we need to discuss for this kind of a diode, which are LI characteristics. The light intensity or light output power with that of the input current. And it is quite clear, during forward bias, as we increase current, automatically there is a linear increase in the light output, the intensity of the light that is going to come out from the diode. So as you increase further, so the intensity is going to increase. This increase would be almost linear in nature. Now, where these materials are used, these particular diodes are used. They are used in numeric displays like the 7-segment displays, and then they are used in traffic signals, LEDs mostly used, and then they are used in emergency vehicle lighting, so like that of our sirens, the police and the ambulances, the camera flashes, flashlights of the camera, and then in mining operations, so the lights that are used so are LEDs only. They would be giving more intensive light with lesser consumption of the electrical energy, electrical power. They are also used in data signaling and also data communication, where data is sent through the fiber cables, and then in flat panel displays. So you might be already knowing them. So there will be an LED TV or something like that, LCD TV. So LED TVs would be, there are two different kinds of LED TVs are there, edge lighting and then the central lighting or something like that. So these are used in those particular flat panel displays as well. So this is all about LED. So we have completed the concept of LED. So light emitting diode. Many a time when I ask questions on LED, people would just say, what is LED? If at all I ask the same question, what they would be coming out in Viva is light emitting diode. It has to be more than that. So when you answer LED, you should say that LED is a diode, in fact, a forward biased PN junction diode made of a direct bandgap semiconductor. Then what would be a direct bandgap semiconductor? You would be answering again, a semiconductor in which the minimum energy of the conduction band coincides with the maximum energy of the valence band for the same value of K. Right? So that is direct bandgap semiconductor. You would also tell me that the transition takes place directly from conduction band to valence band for an electron. So what we call it as a direct recombination or a radiative recombination, since it results in light. So this is all about LED. If at all question comes on LED in the examination, now you are very much confident of writing this one. Never leave this question. This is very easy to write, very easy to understand, and many times asked. Right. We move to the next one. IV characteristics of a solar cell. Right. How many times it has been asked? So it is asked in our curriculum once, twice, thrice, at least in the recent past, and then in JNTU at least once in the very recent. So I am going to discuss now about solar cell. Explain the construction, working and IV characteristics of a solar cell. Just like what we have done for LED, similarly we will be doing it for solar cell. Let us first understand what is a solar cell. A solar cell is basically a PN junction diode which works on the principle of photovoltaic effect. What is that? Photovoltaic effect. Now you know photoelectric effect. What is photoelectric effect? When light is made to fall on a metal surface that ejects electrons. When connected in an external circuit, these electrons would flow and constitute current, what we call it as photocurrent. Wonderful. That is photoelectric effect. Now coming to photovoltaic effect, only one difference. Every other thing is the same. Light falls, electrons ejected, electrons move in a circuit, constitute current, absolutely everything same. Where comes the difference? In the material. If the material is a metal, then it is photoelectric effect. If the material is replaced by a semiconductor, that means if the material is a semiconductor or a semiconductor diode, I mean to say, then that is considered as photovoltaic effect. Photoelectric effect is the material itself is a metal. When this metal is replaced by a semiconductor, and that corresponds to photovoltaic effect. So that means if light is made to fall on a semiconductor, that would produce charge carriers. What do we call it as? Photovoltaic effect. Okay, so what is a solar cell basically? Solar cell is the one, a device you can call it as, which converts sunlight into electricity, right? How does that happen? We'll discuss. This is how we indicate solar cell in a circuit. In the previous case, we have seen a diode with lines, with the arrows coming out. That is for LED. Now here, there is no diode actually. There isn't any diode here we are showing. We are showing a cell here. So a positive terminal and negative terminal of a cell and surrounded by a circle. That is a cell in fact. The symbol, the notation of a cell. Now this one is about light. So it shows that light is falling on this cell, automatically making it to produce current or electricity. So that is how you understand that solar cell, that symbol and notation. Now it is the one that converts sunlight to the electrical energy, right? How it does, we'll see. I'm going straight away to the construction of solar cell. A cell is constructed by depositing a thin P layer on N substrate. We have understood what is meant by substrate and the deposition concepts also. Contact is made to the P layer through the narrow strips so that illumination of the cell surface is not reduced by the presence of contacts. What do we mean by this one? So now let us come to see how that looks like on a bigger scale. Generally, the sizes would be of the order of a few microns. Just see, this is not more than some 300 micron. So this one is somewhere around even less than 1 micron. Why is so? I'll tell you. So N side or N type material is the one that is more thicker in nature compared to the P side. These two are actually made to combine with each other to form a junction. This is the portion of the junction, right? So there has to be metal contacts in order to connect it into an external circuit, right? But that metal contacts should not really come in the way of light falling on the material, right? Where do you make the light to fall on the material? From somewhere, right? Either from this side or that side. Let us suppose we are making light to fall from this side, from the top. This is top layer anyway. So therefore, light has to be absorbed by the material. If at all I keep a complete metal plate on it as an electrode, if at all I use it in the external circuit, then light cannot penetrate. Photons cannot come through that metal plate, right? That's why what we make use is, we're going to keep strips. These are metal strips only, which act as electrodes. So any portion of it would be nothing but an electrode. You can connect between these two. So this is a substrate anyway, that metallic strip would be there at the bottom. On N side there is no problem. On P side, so these strips will be there. So that's what I'm mentioning here. Contact is made to the P layer. Contact of what? The external circuit, right? So is made through narrow strips so that illumination of the cell is not disturbed. Cell surface is not reduced by the presence of contacts. So these are contacts. Still light can penetrate because these are very thin. So light can fall and automatically seep into the material, and thus it can do its duty. What's its duty? We're going to discuss. Is that clear to you? Right, there will be a connection to the external load. So cell is a battery like thing which stores energy, the electrical energy, right? When it is connected in an external circuit, then only it can deliver that energy to the circuit. So there will be the movement of the charge carriers through the external circuit from the higher potential plate to the lower potential plate. So that is what a cell is all about. But it has to store charge. How does it store charge? That we are going to discuss, right? Now, so as a P layer thickness should be less than that one diffusion length, so that the incident radiation should reach the junction region. Right. So we'll go one by one, point by point. The first one, it's quite clear with these values. So this is 300, this is 0.2. The P layer thickness is comparatively very much lesser to that of N layer. Why? Why is it like that? Do you know? Because the light that we are making to fall on P layer should completely penetrate through P layer and fall on the junction, come near to the junction. What do we have at the junction? Because junction is formed, which is a depletion region, which is neutral region. When junction is formed because of combination of p-type and n-type material, that is formed because of the combination of electron and hole at the junction, and also neutralization of the oppositely charged ions from both n-type and p-type materials. Okay, we understood. Now what would light do when it goes to the junction? Through passing entirely through the p region. Light would be in the form of photons, right? Now a photon that goes to a junction, which is an energy particle, can actually can break an electron and a hole. So that electron and a hole which are formed in a covalent bond, it can break a covalent bond to produce electron-hole pair. Electron and hole are produced. Two charge carriers are produced. By what? By a single photon. What does this photon do? This photon goes into the material because it's having higher energy, so automatically hits the covalent bonds at the junction, so which are already found between the electron from n side with a hole on p side. So thus this particular covalent bond gets broken. You're going to have two charge carriers produced, an electron and a hole. Are they going to stay there? No, they are going to move, right? So they would be moving slightly, and since there is no external potential applied, this movement is completely controlled by the strong barrier potential. What is barrier potential? I need not have to tell you, you know that. When we discussed about p-n junction diode, we understood that when the electrons from n side move towards the junction, then there is a loss of negative charge due to this movement of electrons, and thus gain of positive charge. So p side positively charged. Similarly, the n side positively charged, and when holes come from the p side towards the junction, there will be loss of positive charge. That means gain of negative charge. So the n side becomes negative. So n side there will be a negative charge, p side there will be a positive charge. So there will be these two charges. There is a charge separation, there is a potential difference, what we call it as barrier potential. This barrier potential would hinder further drift of the charge carriers towards the junction, because the positive charge on n side will not allow electrons to go towards the junction, because the positive charge that exists then and there itself. Why should electron go towards a hole, go towards another positive charge like a hole and combine? Right? Similarly, the same case with hole. Hole, if at all it wants to go towards the junction, there is a negative charge inside the material itself which hinders it. So it stops it. So therefore, there won't be further drift of the charge carriers. This acts as a, what I mean to say this as, this negative charge on n side and positive charge on n side, which actually having a potential difference, acts as a barrier. That's why we call it as a potential barrier. Right? Okay. I've gone back to to make you understand that. Okay. So there is a potential barrier that is there already without any bias. This potential barrier would control these particular charge carriers and limit them to very close region at the junction. These charge carriers would be formed only over here. So I'd be putting these dots, I'd be putting those particular zeros here. So holes would be over here, electrons would be here. So the junction region is totally packed with the charge carriers that are produced because of absorption of photons. Because each photon that is going to come down towards the junction is going to break a covalent bond, giving rise to an electron and a hole. So a pair of charge carriers are produced by a single photon. So many photons are going to come, being swallowed by the material, automatically more number of charge carriers, there will be more charge that is present at the junction. More charge, more potential between the two ends. Is it not a cell? What do you have a battery as, a cell as? So there will be two different potentials. The ends would be of two different potentials. When you connect it externally, automatically there will be current flow from the higher potential place or point to the lower potential place or point, right? Externally. So this is like the same. It is here there are holes that are deposited. On one side there are electrons. There is a charge separation. If you see one end, so that is positively charged, the other end negatively charged. This is a cell, right? This is solar cell. How these charge carriers are produced? Because of light only. What does the light do? Photons come. Light is in the form of photons. Light is in the form of photons, mind you, right? These photons is going to interact with the covalent bonds and break them. Why covalent bonds occur? Don't ask me now here. We have gone through all that in semiconductors, the first part of semiconductors, right? Okay. So when photons are absorbed by the semiconductor atoms, the covalent bonds break and the charge carriers are produced, electrons and holes. They would stay over here. So the barrier potential is going to keep them near to it. Now, there are many things to understand. The concept of diffusion length. Do you know what we mean by diffusion length here? Diffusion length is nothing but the distance traveled by a charge carrier before its lifetime. The average distance traveled by a charge carrier before its lifetime or in its lifetime. What do we mean by lifetime here? Now, when an electron moves in a material, I mean to say semiconductor, before it gets recombined with a hole, how much time it spends is its lifetime. Lifetime of an electron or a hole is nothing but the time that they can remain without recombining. The time that they can remain without recombining. Once they recombine, so they are not live. So they are already annihilated. They are cancelled. Right? So before recombining, how much time they would live? That is their lifetime. Do you know how much time would it be? Somewhere of the order of microseconds. Not more than that. Even less. 10 power minus 8 to 10 power minus 6 second. Say 100 microseconds to 1 microsecond to 100 microseconds. That's it. Or sorry, not 1 microsecond to 1 microsecond. 0.01 microsecond to 1 microsecond is going to be the lifetime of a charge carrier over there. Right? Now, the distance traveled during this particular time is what we call it as diffusion length, which would be again of the order of a few microns. Micron means 1 micrometer, 10 power minus 6 meters. So the distance traveled by these charge carriers in their lifetime would be of the order of a few microns only. Why should we keep them? So the point here, this point is important. The P layer thickness should be less than 1 diffusion length so that the incident radiation should reach the junction region. Right. What do we mean by this? If at all you make the P layer thickness, P layer being very much thicker equal to the thickness of N layer, photons would be absorbed within the P material itself. They won't reach the junction. And within the P material, if they are absorbed, only holes are created. if holes are created, it's not going to be of any help for us. There has to be electrons that are to be created. That means the photons so fall from the top should reach the junction, also should penetrate into the N region, so that there will be electrons that are created because of the breaking of the covalent bonds. So here also there will be the covalent bonds broken on p side are also n side, and junction region, which is generally, so during reverse bias would be very much thicker in nature. When light falls, the photons fall at the junction, so there will be release of the charge carriers because of the breaking of the covalent bonds. Now, if at all this is thicker, then the photons cannot penetrate. That's why this is made very small, very thin. So it should be less than the diffusion length of the charge carrier. So why this? Suppose a photon falls over here, right, and produces a charge carrier. If this particular, the width of or the thickness of p layer is more than one diffusion length, the charge carrier automatically gets annihilated before it reaches the other side, or n side, or towards the junction. Didn't you understand? I'm going to tell you one more time. Suppose say a photon falls, and it breaks a covalent bond. Agreed? So there is an electron and a hole that are produced. Okay? Now, if this width is more than their diffusion length, automatically before they cross the junction itself, they die. Why? What is diffusion length? The distance traveled by the charge carriers before their lifetime, which would be of the order of a few microns. If this is thick, so the charge carriers before reaching the junction itself, they die. There is no possibility of the charge separation at the junction, and there is no possibility of existence of the potential difference or different polarities across the two ends of the junction. There is no such possibility, no cell, right? So if at all there has to be a cell, there has to be a potential difference across the two ends of the junction. How do we get that particular potential difference across the junction? When we have excess charge carriers on the two sides of the junction, opposite polarities, right? That would happen when this distance is thinner. So automatically the photons would have a chance to go to the junction directly and collide with the covalent bonds or intrinsic semiconductor or the atoms which are there in the bonding, and release electrons and holes. We know when electrons and holes are released, so holes would be coming over here and electrons would be coming over here, and they would be forming so a potential difference across the two ends of that particular diode. So that is nothing but a cell here. That diode becomes as a cell now. Clear? Now, is that clear? So diffusion length. So many people don't write this. They don't even talk about diffusion length. They don't even know about diffusion length. But I want you to be different. I want you to discuss on diffusion length. I want you to put diffusion length when you interpret the solar cell concept, right? So now understood? So why the thickness of p layer should be less than that of the diffusion length of the charge carriers? Because if the charge carrier so produced should be in a position to travel at least towards the junction. That's why if the thickness is less, automatically if the charge carrier is produced at the top, would definitely travel this distance, because this distance is less than the diffusion length. So it would go over here and settle there. Its lifetime. So automatically we know if at all it travels more distance, its life is over. So lesser distance, so life stays on. That means the charge carriers would remain, they live. When they live, they give opposite polarities. When they give opposite polarities, they give potential difference. When they give potential difference, this becomes a cell, right? Now, the photocurrent is due to the EH pairs generated within one diffusion length of the charge carriers on either side of the depletion region. That's what I've been mentioning all the time, right? So on either side of the junction, even though you just see the junction as a thin line here, that doesn't mean that junction region is thinner. So it would be thicker only, right? So, sorry, I'd be using an eraser here. Just give me a second. Okay, so that won't erase. Okay, fine, let it be. So when light falls, automatically there will be charge carriers created, and these charge carriers would be kept by the junction itself, around it or on both sides of it. At what distance? Not more than one diffusion length on either side. So there will be holes here throughout and throughout the P side, and there will be electrons here. So there will be holes here. There will be electrons here on the other side of the junction, giving rise to polarity. Holes on top side, just above the junction. Electrons just below the junction, giving rise to the polarity. Right. Semiconductors with band gap of 1 to 2 eV are used as cell materials. Why? If the band gap is high, we require high photon energy. How can we say so? Suppose say when you draw the energy level structure, CB and VB are here. If this gap is high, the energy would be more. Right? Now, a photon with energy less than that of the band gap is no way useful, because it can never generate an electron at a hole. It can never break a covalent bond if the energy of the photon is less than the band gap. If at all the energy of the photon is either equal or greater than the band gap, then only it can generate electron hole pair. So this band gap actually refers to production of an electron in the conduction band and a hole in the valence band. So if at all they have to exist, electron in CB, hole in VB, there has to be a covalent bond broken. But this covalent bond would be broken only when the energy of the photon is either equal or greater than the band gap. So that's why what we do is, we don't know all the photons will be having that energy or not. Right? Sunlight is falling. We don't know whether this sunlight would be consisting of photons which are having the energy greater than the band gap or equal to band gap. That's why what we do is, we're going to reduce the band gap so that whatever photon falls on, automatically at least it would be having the energy greater than or equal to the band gap. So that's why we consider only those materials with a band gap between 1 to 2 eV. Do you know why I'm mentioning band gap so many times? This actually makes all the difference. See, we have discussed about LED, right? And we have seen what particular colors that are going to come out from LED. And we also understood the color of the light that is going to come out from an LED is completely dependent on band gap, right? So we have written that equation as E is equal to, or delta E is equal to HC by lambda. Lambda is the color of light, the wavelength, which actually is the representation of color of light. E is the energy of transition from conduction band to valence band. Now, if at all we take, the band gap as just have between 1 and 2, then it would be easy for us to make all photons producing electron hole pairs. What we call it as increase of quantum efficiency. Quantum efficiency. Do you know what is quantum efficiency? Quantum efficiency is nothing but the percentage of charge carriers that are produced, the number of charge carriers that are produced to that of the number of photons that are falling on the material. Number of photons that are falling on the material. Suppose that there are 10 photons that have fallen on the material. If they can produce 10 electrons, then automatically the quantum efficiency is 100%. Quantum efficiency, the value equal to 1, which is equal to 100%. All photons actually produce electrons. But that is not going to be the case. Some photons are going to miss out anyway. That's why quantum efficiency can never be 100%. Maybe somewhere of the order of 60 to 70% for the materials. Okay, coming back to the band gap concept here. Do you know the light would be produced from LED when the band gap lies between 1.66 to 3.26 eV. This is a range of the band gaps. So for which the transitions are going to produce light. If the range on either side is breached, you are not going to get light, right? Similarly, when you have band gaps for the materials which are used as for solar cells, very much lesser, automatically more number of photons are going to be used to produce the breaking of the covalent bonds, and thus produce electron hole pairs, thus increase the charge in the material. Now, what kind of materials are preferred for making solar cells? Any idea? Can we use gallium arsenide? Okay, if no, why? Right. So this is about the concept of band gap and about the construction of solar cell. We move further. We discuss about the working of a solar cell. Solar cell is nothing but the one which is not connected. If at all it is connected, it would deliver electricity to the device that is actually connected to. Now, when a PN junction is open circuited, the accumulation of charge carriers reach an equilibrium value, and the voltage across the junction is called as open circuited voltage. Now, let us suppose this to be the PN junction or the solar cell. Okay. Now, here the charge carriers are formed. They would be near to the top of the junction only, within the one diffusion length of the junction. They would remain, giving rise to polarity for that particular junction, and thus to the entire diode, which acts as a cell. Sunlight falls, and this is the arrangement. Now, when this particular one is not connected to any external circuit, so there will be a potential difference that is going to be there between the two ends. There will be a potential difference. That potential difference is what we call it as open circuited voltage, just like an EMF of a battery or a cell. So it is what we call it as open circuit voltage. What is that? Open circuit voltage. What is open circuit voltage? When PN junction is not connected to any external circuit, then across the two ends of that diode, the potential is going to be highest. What is that potential called as? Open circuit voltage. Right. Now you are connected by means of a load, or you are using it for some external device, then current flows. When the current starts flowing, maximum current flows initially through the load. This maximum current, when you short circuit this two ends of that particular diode, is what we call it as short circuited current or short circuit current, whatever it is. So there are two parameters for a solar cell. One is open circuit voltage and the other one is short circuit current. So these two are important. What is open circuit voltage? The voltage across the two ends of the diode when it is not connected to any external device. Right. When you connect it via a load to an external device, current starts flowing through it, and the current would be maximum. Right? There are two things. So the voltage when there is no external circuit is connected is what we call it as open circuit voltage. Without connection, so what we call it as open circuit voltage. When you short it across the two ends, current would flow. That is called as short circuited current. So you got two terms, open circuit voltage and short circuit current. Clear? Now IV characteristics of this solar cell. So we'll be having voltage on x-axis, current on y-axis, and they would be like this. So why? When current, the circuit is open, maximum voltage would be there. That is what we call it as across the junction, across the two ends of the diode, what we call it as open circuit voltage. When the circuit is connected via a load, shorted via a load, current flows and the current would be maximum. What we call it as short circuit current. The region between these two is the one of our importance. So here, as the voltage changes, automatically the current slowly falls, and for the voltage reaching the open circuit region, actually this is like this way. So this is in the third quadrant. Suppose if at all I have to show this one, sorry. I have to show this in the third quadrant. So how to show this one? This would be like this. Right? This is voltage and this is current. So this is VOC and this is ISC. But that we are showing it in the first quadrant. How it would be? Like this. So this is ISC and this is VOC. Okay. Anyway, whatever may be the quadrant, the concept remains the same. Okay. Now we are going to consider the maximum power point. The maximum power point is nothing but the point which would be consisting of maximum values of voltage and current, because we know power is the product of voltage and current. Here, and this exists exactly at the knee of the graph. As you see, this one actually like knee. So somewhere here the maximum power point is going to occur. So that is, this corresponds to IM. When you draw lines taking that graph onto both x and y axis, you're going to find Vm. So when you draw a line onto x axis, the x-intercept being Vm and the y-intercept being Im. The product of these two is what we call it as Pm, the maximum power. Now there is one important parameter for the solar cell, what we call it as fill factor. How we term it as? Fill factor. So fill factor is the one that is defined as, I would write it as FF, defined as the area of maximum or larger rectangle. We put it that way. Okay? Area of the larger rectangle within the curve. Curve means the center portion divided by the product of ISC and VOC. Area of the larger rectangle, so that means we have drawn rectangle and we have got the coordinates of the rectangle as IM and VM. So it is nothing but the ratio of product of IM and VM to that of the product of VOC and ISC. This is going to give us the fill factor. Generally this fill factor would be between 0.65 to 0.8 for a solar cell. So that would be of the order of 0.65 to 0.8. What is fill factor? Area of the largest rectangle divided by the entire area of the curve, under the curve. So which is nothing but the product of ISC and VOC. So you can consider that way. Area of the largest rectangle divided by the entire area of the curve. What does this largest rectangle give us? It is going to tell us that this entire area is going to give us that the maximum amount of power available with the solar cell, and this particular rectangle is going to give us the maximum power that we can drive from solar cell, that we can elicit from solar cell or derive from solar cell. Maximum power that we can derive from solar cell given by this one, and the entire power that is available with solar cell is under the by this particular curve. So the area under this curve is going to give us the total power that is available with solar cell, but this particular rectangle is going to give us the maximum power that we can drive or derive from the solar cell. So that ratio is nothing but fill factor. Clear? Okay, so these are IV characteristics. Now it's quite evident that if you increase the number of photons, more electron hole pairs are generated, more would be the current. So which can be given by means of this graph. So just observe the values of the optical power. This is optical power, that means the light intensity 50. So this is the value of ISC. For 100, this is the value of ISC. For 150, this is the value of ISC. That means as you increase the intensity of the photons, I mean to say the sunlight, or the optical power, thus there will be increase in the output of the solar cell also, in the way of it increase in its current, right? So this is about the VI characteristics of solar cell. Moving further, where solar cells are used, there are many. They are used in satellites and space vehicles. Solar cell is mainly used in satellites, the artificial satellites. How the artificial satellites move? They have to get energy, so they'll be having solar panels. Sunlight would be absorbed by these solar panels and automatically they would store. During the time when there is no sunlight, so using the energy from those particular cells, that particular satellite would move around the earth. They are also used in power calculators, watches and mobile phones, we know that. So there will be a solar panel in calculators or the watches that we make use in. And they are used in also commercial electricity. Nowadays, actually commercial electricity, the solar panels are quite regularly used, even for domestic production of electricity. But so on a smaller scale. In water heaters also, solar water heaters, everywhere solar panels are there, they're useful for these particular applications. So these are a few applications of solar energy and the solar panels and solar cells, which actually store that energy. So we'll move further to discuss about the third of this particular class, which is the principle and working of a pin diode. Right, pin diode. So just we move on to pin diode. So this is the frequency with which this question has been asked in the recent past. I have considered only the recent examinations, possibly 22 and 23 examinations. So this is its frequency. Right. Now, just before we go for pin diode is a photodiode. Pin means positive, intrinsic, negative. Positive, intrinsic, negative. But before we get to understand pin diode, we need to understand what is meant by a photodiode. Okay, I'll just give you an introduction of what is a photodiode, and then we move to pin diode. A photodiode is essentially a reverse bias p-n junction diode, which is designed to respond to photon absorption. Generally, photodiodes are used where there exists photodetection, light detection, which are generally at the receiving end of the fiber communication system, an optical fiber communication system. An optical fiber communication system would be consisting of a transmitter followed by or connected to a waveguide, which is an optical fiber, and then that is connected to a receiver. At the receiving end, light would be received by a device. Light would be detected by a device, what we call it as a photodetector. Photodiode is such photodetector. It would respond to photon absorption. Next. Right. So it consists of, what is the construction of a photodiode? It consists of a p-n junction diode and embedded in a clear plastic capsule, which light is allowed to fall only in one direction. Just like solar cell, it is actually capsulated. There will be a thin p layer surrounded by an n layer, and there will be metal contacts on both sides. Light is made to fall onto the junction via this thin p layer, where light is going to go and actually create electron hole pairs. So these electron hole pairs are created just like solar cell. Solar cell, once connected, then only it would work. But photodiode, now because it is producing the charge carriers, if at all connected externally, so automatically there will be change in the charge linked with the external circuit. That is nothing but detection. So it is detecting light. Suppose say if you connect photodiode in a way that the two ends are connected to a sensitive galvanometer. If galvanometer shows a deflection, what does that mean? That means there is light falling on the photodiode. When light falls on the photodiode, automatically there will be charge carriers created. These charge carriers would move through that particular galvanometer and change it and give deflection to it. Is it not light detection? That is what, in principle, what the photodiode does, right? When the diode is not illuminated, small reverse current flows due to thermally generated minority carriers, which is independent of the applied reverse voltage, called as dark current. This current is proportional to the concentration of minority carriers. This is not new for us. When we have discussed about the p-n junction diode, we have discussed about the reverse bias. In reverse bias, we say there is no current. But strictly speaking, there is no current due to majority carriers. There is current because of minority carriers. Like the electrons on p side and the holes on n side, due to reverse bias, they cross over the junction. Right? Just give me a second. 5 to 9:20. Thank you. So the current is proportional to the minority carriers. So that means there will be current. If you ask me strictly, there will be current because of minority carriers. Okay? And this current is a constant current, what we call it as reverse saturation current. So when a diode is not illuminated, generally photodiode works in reverse bias. So when there is no light falling on the diode, there will be current only because of minority carriers, and which is constant. And this current is what we call as dark current. This is called as dark current. But when photodiode is illuminated with light, automatically the charge carriers are created at the junction. As I told you that each photon would be absorbed just like solar cell. So there will be charge carriers are created, and these charge carriers flow, giving rise to more current. But this is a current that is produced because of light. When there is no light falling on it, still there will be current, what we call as dark current. But that is because of the minority carriers flowing across the junction, which is very, very less, of the order of a few microamperes. Right. Moving further. So now we are going to get to pin diode. What does pin diode do for us, or what our understanding of pin diode should be? Pin diode would be consisting of a p region and an n region. In between, there is a large intrinsic region. We know p-type material and n-type material are the extrinsic semiconductors that are made by doping impurities with the intrinsic semiconducting material. P plus is nothing but a material with heavy doping of the trivalent impurities, the acceptor impurities. Thus, there will be more number of holes, what we term it as P plus region. Similarly, N plus region, there will be more number of electrons because of heavy doping. So P plus N plus regions are separated by a very thick intrinsic region. Intrinsic region means an intrinsic semiconductor. What does this intrinsic semiconductor do? We know one thing about intrinsic semiconductor. It will not be having free charges under normal conditions. We know what is an intrinsic semiconductor. A semiconductor in which charge carriers are produced only by increasing temperature. If you don't change the temperature, the charge carriers remain so. Their value is not going to increase, right? So that means generally intrinsic semiconductor will not be having more charge carriers at normal temperatures. Okay. Now coming back to this one, the P layer, intrinsic layer and N-type layer are sandwiched to form two junctions, Ni junction and Pi junction. Ni means the N-type and intrinsic layer. Pi means the P-type and the intrinsic region. So somewhere here, or else this one. There will be an ohmic contact in between. So there will be a slight change as far as the two sides of the junction, intrinsic region is concerned, P plus and N plus. As far as the concentration is concerned, the number of charge carriers are concerned. So that's why there is another layer that is involved. Okay, don't worry about it. Consider this to be the Pi and this to be the Ni junction. So there are two such junctions, Ni junction and Pi junction on both sides. The P and N regions are heavily doped and they are used as ohmic contacts. So they can be used as ohmic contacts, means as an external circuit. This is the positive side and this is the negative side to the external circuit. Right. How do we operate pin diode? Reverse bias. Remember that. In reverse bias. Right. There is large thing that we have to discuss, but just before that I would be discussing what would happen if the pin diode is connected under reverse bias? Then I'll make you read this. Okay, fine. We know P plus is going to have excess number of holes, N plus is going to have excess number of electrons. Here N is given, okay, number of electrons would be more. And then here I region is the intrinsic region. There are two junctions, one here, what we call it as Ni junction, there is Pi junction, right? Now when we increase reverse bias, so it is connected in reverse bias. So P type is connected to the negative terminal and N type is connected to the positive terminal. When we connect that way and increase the reverse bias, what would happen? So these junctions are going to grow in size on both sides. And there is a stage reached where this entire intrinsic region is becoming a depletion region. We know in reverse bias, the depletion region length is going to increase. So since there are no free charge carriers in the intrinsic region, so the charge carriers on P side are going to sweep away towards the negative terminal here, and the charge carriers on N side, which happen to be electrons, would be swept away from this particular portion towards the positive terminal of the battery. So this particular region would be having the depletion region. Let me tell you that the depletion region length or the width is going to be more in the intrinsic region compared to that of either P side or N side. I repeat, the depletion region width is more in the intrinsic region compared to that of P side or N side. Thus, so there may be a stage reached where this entire intrinsic region becomes depletion region. What does it become? Depletion region. When it becomes depletion, why we have to make that depletion region? In order to make it photosensitive. In order to make it photosensitive. What do we mean by that? Suppose if you have a depletion region of larger width and make light to fall on it, more area is available for photon absorption. Agreed or not? Now suppose if this layer is very thin, the junction is, if you use only PN junction diode, then there will be a thin layer at the junction. If you can increase that thickness by applying the reverse bias, agreed. But still the thickness would be very small. Light has to fall on the junction so that the charge carriers are to be produced, and that is how the light would be detected. Charge carrier production gives rise to change in the current linked with the circuit. Thus there is detection of light. Okay, that is what we call it as photosensitive nature. So light, if it falls, that would be sensed by this particular device, and that gives a change in the parameter like current or voltage. Right? Now if I make that region larger, bigger, then automatically more light is going to fall on that region. Agreed or not? Small region, lesser light. How much light you make it? So it doesn't cross that area, is it not? So if the area is larger, more light is going to fall. And if more light falls means more photons are going to fall. More photons means more electron hole pair production. Right? For even little amount of light that is falling on the material, there will be photons that are going to fall, and thus give rise to more number of charge carriers, and thus more current in the external circuit, and thus more photosensitiveness. Agreed or not? So there will be, the deflection will be like this compared to that of a junction diode deflection, more possibly like this, slight deflection in the junction diode, in the external voltmeter or ammeter or galvanometer. Now when you use pin diode instead of PN junction diode, because of this region, even for lesser light or low intensive light, all the photons that fall would automatically be absorbed by this area of the material, and all these photons would result in the breaking of the covalent bonds, releasing electron hole pairs, and these electron hole pairs, when they travel in opposite directions constituting current, that would be detected by the ammeter or microammeter, whatever you connect it to the external circuit. So this is photosensitive nature. Pin diodes are specially designed for it. That's photosensitive nature itself. You need to also understand that in this particular intrinsic region, there is no recombination of electrons and hole pairs take place, even though so the region is quite larger, and the lifetime of the charge carriers is also very less, and the depletion I mean, what we call it as diffusion length is also very much lesser for the charge carriers. But still, they would flow because of the large reverse bias. You would apply reverse bias, larger reverse bias for smaller lights, very less dense, very less intense lights also can be detected. Because high reverse bias is there, as and when light falls, automatically in the depletion region, the intrinsic region happens to be the depletion region, light will be absorbed, more charge carriers are produced, each photon is going to produce charge carrier, quantum efficiency is high, and these charge carriers would move in the opposite directions. Suppose a hole is produced, we know hole would be moving towards the negative terminal of the battery, and an electron is produced, so we know the life ambition of an electron, it would be moving towards the positive terminal of the battery. So thus, they are going to actually constitute current. So automatically if you keep some micro ammeter or a sensitive galvanometer, so there will be deflection. This is photo detection. This is photo detection. We are detecting light. Understood? This happens only when light falls. Okay? So that is the specialty of PIN diode over a PN diode. So this intrinsic region is going to help us because that is going to develop into a depletion region, and larger depletion region with higher reverse bias, automatically very little amount of light, very little intense light can actually produce more current, and thus photosensitivity to the particular device. So this is all about PIN diode, right? This is what I've given it over here. So the depletion region, electrons that are produced, generally they would diffuse in opposite direction during reverse bias. But once light falls in the depletion region, what would happen? So a hole and an electron would be moving in the opposite directions because they are reverse biased. So the P region is now connected to the negative terminal and N region is connected to the positive terminal. So electron has to move in this way towards N region itself, constituting current. So this is all about the concept of PIN diode. Now let us read this one. When the reverse bias is applied to PIN diode, the width of the depletion region starts increasing in the intrinsic region. That is what I have told you. So the width of the depletion region is going to increase within the intrinsic region. And with the increase of the reverse voltage, width increases even more, and a stage is reached when the depletion region width becomes equal to that of the thickness of the intrinsic layer. That means the entire intrinsic layer is going to become depletion region between P and N type materials. So more light can fall, right? Because more area is available. And thus, even for smaller light also, the charge carriers can be generated, and that is photosensitiveness. Is the photosensitiveness increased compared to that of the normal junction diode, PN junction diode for PIN diode? You're right, yes is the answer. That is because of existence of the intrinsic layer. So the intrinsic layer is swept free from all mobile charge carriers. Initially that is what is going to happen. Because of the reverse bias, all mobile charge carriers would go away from it. But when light falls, the charge carriers are produced, move in opposite directions, constitute current, detect light. This is what I just want to show you. So this is what we call it as dark current. So the current would be lower. This is in the third quadrant, right? So as you increase voltage, the current is going to increase up to a particular value and remains same. So what we call it as saturation value. So this is the saturation value, right? So this is under no light conditions, dark conditions. That's why the current is less. If you increase the light intensity in the order of lux, lux means luminous flux, that is actually the measurement of luminous intensity. So 1 lux, 1.5, 2 lux, 2.5 lux, and so you can see the current has increased, the saturation current has increased drastically, increasing the photosensitivity of the material, right? So this is about a photodiode. Is that clear? Is this diagram clear? So this is for no particular light under dark conditions. This is when you increase current in the different regions. I mean, the increase light intensity, the current also increases. Right, what are the applications? These are used in light detecting systems, not light detection, light detection, mind you, okay? They are used in light detecting systems, and then reading film soundtracks, these are the ones that are used, the pin diodes and the photodiodes, light operated switches, so based on light switches which will be on and off, so the light intensity would actually decide things, and then high speed reading of the computer punched cards and tapes, and at the receiving as a receiver end of the fiber optic communication system, these diodes are used. This is all about the pin diode. Now how much time we have? 5 minutes. We need to finish BJT. We will finish BJT. Okay? Explain the principle and operation of a BJT, bipolar junction transistor. So this was also quite frequently asked in the recent past, very important as far as examination is concerned. So I would be moved to discuss about bipolar junction transistor. What we mean by bipolar junction transistor? A bipolar junction transistor is a 3-terminal semiconductor device used to amplify electronic signals to switch electric power. So 2 ways it can be used as. 1, to amplify, or 2, to be used as a switch. This is how it appears, 3 terminals, right? 3 terminals I would show with some other color, right? These are the 3 terminals. This is another way, right? It consists of 3 regions, emitter, base and collector. This is how it would appear. Emitter, base and collector. Okay, this is base, this is emitter, this is collector. The circuit symbol of the transistor would be like this. So there will be a circle, okay, and then there will be 3 lines. So this is the base line, and there will be line like this, there will be line with an arrow. This is nothing but emitter. Line with an arrow is an emitter. The arrow can be inside or outside. So that is for base, and base would be like this. This is emitter and this is collector. Okay. Now terminals of a transistor. There are 2 different types of transistors. How these transistors are formed? When you sandwich second type of semiconductor into one type of semiconductor, then automatically you would get the 3-terminal device. Say sandwiching a P layer in between 2 N-type materials. I mean to say, in an N-type material, if you sandwich a P-type material, so you're going to get NPN. Similarly, if you sandwich a P layer, N layer in a P-type material, you're going to get PNP transistor. If you sandwich N-type material into a P layer, you'd get PNP transistor. So now I'm discussing NPN for convenience. Okay. It would be consisting of emitter, base and collector. Emitter is the one that supplies charge carriers to the base, and this is a heavy doped region. Base is the one that is lightly doped and thin region, and that controls flow of charge from emitter to the collector. And similarly, collector is another terminal which is moderately doped but a wider region compared to that of these 2. This is thinner and this is so thick but not that much thick as that of collector. It is moderately doped wider region, collects charge carriers from the emitter through the base. Now this is how we represent the 2 types of transistors. This is NPN transistor and this is PNP transistor. This is how we show it in circuit symbol. This is how we show it in the circuit symbol, as a circuit symbol in the circuit. Okay, just give me a second. Right. So this is NPN transistor connection in a circuit. When we make use of this when we discuss about the working. Now this is nothing but an NPN transistor. This is the emitter, this is the base, this is the collector. And this is emitter current IE, and this is collector current IC, and this is base current IB. There will be two particular power supplies, batteries you can say. One is VEE to forward bias the emitter base junction. Other one is VCC to reverse bias the collector base junction. I will explain this one when we discuss about the working of a transistor. Right. Now we are going to discuss working of NPN transistor. Now the N region is emitter, P region is base, and N region is again collector. Now these are connected in a way that the emitter is N type, base is P type. There will be a junction formed between these two, which is a PN junction. This is forward biased. The emitter base junction is forward biased. So the junction between emitter and base is called as emitter base junction. The junction between collector and base is called as collector base junction. Right, the emitter base junction is forward biased. How do we do it? So we connect this way, and there we want to measure the current, what we call it as emitter current, by means of a milliammeter, that is this one. So the negative terminal is connected to N side and the positive terminal connected to P side. And we would be actually reverse biasing the collector base junction, just like this. So the collector, which is N, is connected to the positive terminal, and the base, which is common to both this side and that side, is now utilized to connect as to the negative terminal. Understood? So this is reverse biasing of the collector base junction. Base, this one is the collector base junction, and this is the emitter base junction. Now because of the forward bias, emitter base junction would be thinner compared to that of the collector base junction. So because of the reverse bias, so we know the junction would be, depletion region would be increasing. Now let us understand how does this particular one works. Right. There will be current, that is the emitter current, that would be in this particular direction. There will be collector current, that is into the collector, and the base current into the base. Why? What is the direction of current? It is direction opposite to the flow of electrons, the conventional current direction. Now when you see the forward bias here, automatically the electrons would go in this particular direction. What should be the direction of current in the emitter? So that should be this way. So this is the direction of emitter current. Right. Now coming to base. So base would be consisting of holes, right? But the electrons that would enter from the emitter into the base would automatically flow through this closed circuit through base towards the positive terminal. That means the electrons are going in this particular direction. What should be the direction of base current, which is conventional current? So exactly opposite. Similarly, now electrons from emitter would be entering into the positive terminal here because of the reverse bias. So that means the current should be this way, the collector current. Right. Now we have understood the directions of the emitter current and the base current and collector current. Now I would be explaining the working of this transistor. Now since the current, the forward bias is applied to emitter base junction, the electrons would move into the base region through this junction, which is very much thinner because of the forward bias. And 95% of the electrons would travel through this one. Only 5% of electrons would be either combining with the holes or would be staying at the region. Because base region is very much thinner, it cannot hold all the electrons. So the electrons, because of their pace due to the forward bias, would cross over this base region and enter into the collector region through this particular depletion region. Now these 5% of the electrons would either recombine with the holes in the P region or they would flow as base current into the positive terminal of the battery. Here VEE. VEE is called as the supply battery for emitter base junction, or simply emitter. VCC is nothing but the supply battery for the collector. Now let us talk about say 100 electrons going from the collector, 5 electrons would be there in the base region, which happens to be the p region, and all these 5 electrons would travel to the positive terminal of the battery. Now other 95 electrons would cross over this junction and enter into the n region. This junction is much more thicker because of the reverse bias. Even then also, we know during reverse bias the charge carriers cannot cross the junction, but here the electrons would be here, 95 number electrons would be there. These electrons are in the p region, which are minority carriers. We know during reverse bias minority carrier drift takes place through the junction. So therefore these electrons which are minority carriers in the p region can travel through the entire junction and reach the collector region, and thus in this collector region they travel as collector current into the positive terminal of VCC. This is how there will be current flow through the entire transistor. Now as far as the movement of electrons is concerned, just observe. Let us consider the current in the emitter is IE, the current in the base is as IB, the current in the collector as IC. General case is that when we have the forward bias, there will be more current, so automatically, and when we have reverse bias, there is less current. That means when this particular region is forward biased, the emitter base junction, that means the emitter current should be high. Similarly, the base current should be also high because of the forward bias. Now when you consider this region, the collector region is reverse biased, so therefore the collector current should be low. But that is not going to be the case. As you have just understood, if 100 electrons start from here, 100, then 5 only would be with the base, other 95 would be with the collector. That's why the emitter current, which is a combination of the base current and the collector current, would be almost same, almost equal to that of the collector current, not the base current. This is the speciality of the transistor. Shall I come again? Now, under normal circumstances, when you see two PN junctions, one is forward biased, the other one is reverse biased. So we know through the forward bias junction there has to be large current. What are the currents that are present in the forward bias region? IE and IB. They should be very large, right? That should be the case. Similarly, the reverse bias region you have IC. In the reverse bias region you have collector current IC. So we know under reverse bias the current should be very small, very less, right? So that means if at all we compare currents, IE should be largest, IB should be second, and IC should be third, right? Should be, but that is not the case. What is happening? Generally that is the case, but in case of this particular device, what we call it as transistor, so the current, the emitter current and the collector current almost match with each other, making the base current very less. Why this happens? Because 100 electrons start from emitter region, because base being very much thinner, so, and very less number of electrons would be having a chance to stay here and combining with the holes and constitute the base current. The other electrons would travel to the collector region even though there is a large reverse bias, but this is because of the fact that the electrons would be starting from the p region as minority carriers, and there is every possibility that these minority carriers can drift through the junction during reverse bias, and these electrons, once they reach the collector, they would flow with other electrons that are there in this region as collector current. Understood? So this is the speciality of the three-terminal device, what we call it as a transistor. Shall I tell you a thing here, why it is called as a transistor? Now generally transistors are used to be as an amplifier, to amplify signals. Amplification means, suppose a AC signal is connected here, an AC. I'm going to come back to this color. Now that would be like this, a sinusoidal. At the output, if you have a load, if you keep a load, then automatically the output would be of this form. That means there is increased strength of the signal, increased amplitude, increased intensity of the signal. This is what we call it as amplification. Increasing the strength of the signal is what we call it as amplification. This is used as an amplifier. Why? Because the signal would be traveling from a region of low resistance to a region of high resistance. How can we say so? Is the signal traveling from a region of low resistance to the region of high resistance? Yes. This region is forward biased. Forward bias means conducting path, means low resistance. This region is reverse biased, means non-conducting path, means high resistance. Is the signal is traveling from the region of low resistance to the region of high resistance? Yes, it does. It travels through the entire transistor. That means if you connect an AC signal to this particular transistor, it would travel from a region of low resistance to region of high resistance. There is trans resistance, change of resistance, transistance, transistor. Understood? So the signal would be traveling from a region of low resistance to a region of high resistance. That's why we call this one as a transistor. Transistor is a three-terminal device, agreed, consisting of emitter, base and collector. All that are correct. This would be used as an amplifier generally when we use AC here. AC means alternating signal. It is going to increase the strength of the signal. Quite simple. How come? Because the strength of the signal at lower resistance region would be less, and when it goes to the high resistance region, it would increase. Why? Because V is equal to IR. For a lower value of currents here, automatically you would be having lower signals. Since R is increasing, so V is going to increase. So that is how there will be increase in the value of the strength of the signal. This you can understand when you actually study these particular materials and their concepts during your electronics papers, electronic subjects. Okay. Now coming back to the NPN transistor, the current conduction and current control is controlled by electrons only. The current conduction is carried out by electrons only. Inside this entire transistor and outside also, electrons would travel through. So as you see, so electrons would travel from the base electrons would travel from the emitter to the base into the collector. Electrons, right? And they would are the ones which would travel also in the external circuit. So the current conduction is entirely carried out by electrons in NPN transistor. Similarly, for a PNP transistor, inside this transistor, holes are the charge carriers that move, and outside electrons. Outside holes cannot move. Only electrons would move in the connecting lead, through the connecting leads into the batteries. Suppose an electron comes out from the collector region and so automatically gets absorbed in this positive terminal. At the same time, an electron is produced and passes into the emitter region. Thus, so the electrons number would remain as it is. So there will be continuous conduction by this one. Shall I repeat? Suppose say you might have a question that as electrons enter into the positive terminal of the battery, because that is their life ambition, all the electrons would automatically dry out of the material, right? And that's why I am telling you, for every electron that actually gets absorbed into the positive terminal of the battery, there is another electron created at the negative terminal of this battery which enters into the emitter region. So automatically the electron number all the time remains same. There will be continuous conduction. This is how NPN transistor works, and that is how it is used as an amplifier. With this, we close the second unit. And the important questions correspond to the second unit. I am thankful for the opportunity given to me to discuss the first and second units, the important questions with you. I wish all of you very best. to do well in the examinations with whatever little I could discuss with you, I could share with you. Make a best use of it and good luck. All the way. Thank you very much for the interest, time and patience, support that you've been giving to us. Thanks a lot. Good night.